Hey everybody, I'm sorry I'm not with you today. We're going to do this lesson. I believe this is day 9 in your syllabus. Notice the title, Discontinuities. Remember that means where a function is not continuous in the graphs of piecewise functions. The goal of this lesson is to predict without graphing. The behavior of the graphs of the pieces in relation to each other. There are 3 different scenarios that can occur. So we're going to draw an example of each one. Let's look at the first one. I want you to just make a little XY axis, and we're going to do that in each of these 3 boxes. I hope those are not terribly crooked. Look at the first one. The pieces can connect at a closed circle at x equals a. I'm going to let x equals a be right there. Now, so what we're having, the fence is like right there. Now remember, the fence is not a part of the graph. It's just a visual aid for us. So the pieces are going to connect at a closed circle at x equals a. So let's just say one of the pieces looked like this. And the other piece looks like this. The pieces are connecting at a closed circle when x is equal to a. Now I want you to notice, if you put your finger or your pencil on this graph starting at the far left and you trace the whole thing, you would never have to lift your pencil. That function is continuous. Look at the second one. The pieces can connect at an open circle at x equals a. Again, I'm going to put in my fence, but the fence is not a part of the graph. So let's say the graph looks like this. So the pieces are connecting at an open circle at x equals a. Now if you tried to trace this graph from left to right, you would have to pick up your pencil when x is equal to a. So I know that this function is not continuous or discontinuous when x equals a. Last one. The pieces cannot connect with each other at all at x equals a. So you might have something like this. If you trace that in order from left to right, notice again you would have to lift your pencil when x equals a. So this one has a what we call a discontinuity, or the function is discontinuous at x equals a. The latter 2 of those 3 scenarios, so the last 2, are examples of functions that have discontinuity, means they're not continuous. Before we take a look at graphs that have discontinuities, let's investigate one function in which there is no discontinuity, meaning you never have to lift your pencil if you graphed it. That is a function whose pieces connect at a closed circle, just like the first graph we did above. Now the first thing we're going to do is draw this graph. Now notice you got fences at x equal -5 and at x equals 0. Again, please remember the fences are not part of the graph. I'm going to draw this one in red. So what have we got there? We've got a parabola that's been shifted left 3, up 4, and it's reflected over the x-axis. So left 3, up 4, so you got a vertex there, and reflected over the x-axis. Now, I think I showed you guys the other day, if you have, and I'm going to have to just erase this for a minute, just the regular old x squared, 0 squared is 0, 1 squared is 1, 2 squared is 4. Look at the movement to get from this point to this point. Right 1, up 1, then right 1, up 3. Then the next point, which is at 3, 9, would go right 1, up 5. That's the pattern in a parabola that has not had a vertical stretch or shrink. So I'm going to use that pattern here, except I'm going to open down. Right 1, down 1, right 1, down 3. I need to get that fence back in, don't I? Right 1, down 5. Now, does this red guy own that fence at x equals 0? No, does not own the fence. Open circle. Now let's go the other way from the vertex. Left 1, down 1, left 1, down 3. Does he own that fence? Yes, because there's a closed, there's an or equal to there on the -5. Now the other side, that's an absolute value. Shifted what, right 2, down 7? Opens up. So on one side, it's got a slope of 1. The other side has got a slope of -1. Now notice, as we're going left, my graph of this absolute value is going to land on that open circle. Because of this, we know that this guy owns the fence. So his closed circle will fill in that open circle. This function is continuous at x equals 0 because if I graph this function from left to right, I never have to lift my pencil. Now let's look at these questions starting up here. The first piece of the graph of q of x will end just shy of. All right, I guess I'm going to try to trace this so you can see. Let's trace it with green. This graph, this piece, does not touch the fence, remember? So that piece ends just shy of x equals 0. And the second piece actually starts at x equals 0 because that second piece owns the fence. Now, second question. Is q of x defined at the x value where the first piece ends and the second piece begins? So the question is this function defined right here when x is 0? That's where the first piece ends and the second piece begins. Yes, it's defined because somebody owns the fence there. So q of 0, well, what is q of 0? Well, look at the graph. Q of 0 is -5. Now you could also do that by plugging in here because that's the equation that owns the fence. 0 minus 2 is -2. Absolute value of -2 is 2. 2 minus 5 is -7. Now you're going to learn some new notation here. This is probably, and I'm looking right here, how you wrote end behavior probably when you were in Algebra 1 and 2. But you didn't see anything like this. Now I want you to look right there. That says as x approaches 0 from the left. What that means is x is approaching 0 from numbers smaller than 0. So x is approaching 0 from this direction. Now, as x approaches 0 from that direction, the question is, what are the y values doing? Well, let's trace. As x gets closer and closer to 0, the y values are getting closer and closer to -5. As x approaches 0 from the left, or excuse me, sorry, as x approaches 0 from the right, that's what the plus sign means, from the right, from numbers bigger than 0, what does the graph do? So we are coming at x equals 0 from the right, from numbers bigger than 0. Let's just trace it. As x is getting closer and closer to 0 from the right, look right here, the y values are also approaching -5. So again, let's just read, what does this say right here? As x approaches 0 from the right, that means as x approaches 0 from numbers that are bigger than 0, then the graph of q of x is approaching -5. Now I need you to understand, on this one, as x approached 0 from the left, from numbers smaller than 0, the graph approached -5. Now it never got to -5 because we had an open circle there, but it approached, and the approach means got closer and closer, but it didn't have to touch the -5. Maybe it did, maybe it didn't, but it got closer and closer. So let's look at this last question on this page. Using the equation of q of x, determine the y values that each piece approaches from the left and the right of 0. So here's what we're going to write. As x approaches 0 from the left, the function, which is q of x, approaches. Now, let's see, it says to look at the equation, so we're not looking at the graph right now. We know what the answer is supposed to be. It's supposed to be -5. But can we get that from the equation? What you have to decide is which one of these sets of constraints have the numbers that are smaller than 0. Well, it's this one right here. So from the left of 0, we're going to be using this equation. Substitute in 0. You say, but he doesn't own 0. That's okay. What we're doing is, as x is getting closer to 0 from the left side. So if I put 0 in here, I have 0 plus 3 is 3, squared is 9, opposite of 9 is -9, plus 4 is -5. Look, that's what we got right here. As x approaches 0 from the right, from numbers bigger than 0, what does the y value get closer and closer to? Which of those sets of constraints has the has the x values that are bigger than 0? Well, these have the x values that are bigger than 0. So I'm going to use this equation. Substitute in 0. 0 minus 2 is -2. Absolute value of -2 is 2, and 2 minus 7 is -5. And look, that's what we got right here. What you just found in calculus, this is what we're doing right now in calculus, it's called a limit. It means we might get there, but we don't necessarily have to get there. Next page. Oh, wait. So let's go back and talk. This graph, this function, if you'll notice, there was no discontinuity. This function was continuous. Now, I want you to look at why it was continuous. Look at two things. When x equaled 0, the y value was -5. We got it right there. And as x approached 0 from the left and the right, we also got -5. When that limit is equal to the same thing as the y value, that function's continuous at that point. The angels are singing now a little bit. Next page. There are two kinds of discontinuities that we're going to deal with. One is called point discontinuity. And a point discontinuity happens when two pieces connect at an open circle. And you have a jump discontinuity. And that happens when the two pieces don't connect at all. If I could spell, that would help, wouldn't it? Let's look at these four graphs that are on your page here. And let's decide if each of these graphs is a point discontinuity or a jump discontinuity. So let's look at F. Now I'm tracing and tracing and tracing. Haven't had to lift my pencil yet. Oh, I got to lift my pencil. Notice, here's the rest of it. Now, is it a point discontinuity or a jump discontinuity? Do the two pieces connect at an open circle, or do the two pieces not connect at all? Well, they don't connect at all. So this one, I have a jump discontinuity at x equals, and your discontinuities are always at an x value, at x equals 3. Look at the second one. We trace, we trace, we trace. Whoop! The rest of it's over here. Point discontinuity, do they connect at an open circle? Or a jump discontinuity where the two pieces don't connect at all? Yeah, this is another jump discontinuity. And that happens at x equals, I believe that's -3. H of x. I'm going to trace left, 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 left. Whoop! I got a discontinuity at x equal -1. Do those two pieces connect at an open circle, or do they not connect at all? Well, they connect at an open circle. So this is called a point discontinuity at x equals -1. Last one. Oh, I got a problem right there. Do those pieces connect at an open circle, or do they not connect at all? Well, they connect at an open circle. So that's a point discontinuity at x equals -3. Now you say, but what about this? That's not a problem. They still have a point, or this graph still has a point discontinuity at x equal -3 because those two pieces connect at an open circle. Now I'm going to stop for a minute and I'm going to erase this stuff because on the next page we'll be coming back to this page. So I'm going to erase for a minute. Now the only stinky part of this is that we have to keep referring back to those graphs on the previous page. So I'm going to have to keep going back and forth. We're going to complete the following tables of information using those four graphs. So we're going to start with f of x, which is the one in the top left corner. What type of discontinuity occurs in the graph of f of x? Now we said that was a jump. At which value of x does it occur? Well, that occurs at x equal 3. We did that already. Now look at this question right here. Is f of x defined at this x value? When x is 3, does x equal 3 have a y value? Nope, because both of those are open circles. So f of 3 is undefined. Next question. By investigating the constraints of the equation, the first piece of the graph of f of x will stop just shy of, that graph stops just shy of x equal 3. And the second piece starts just past x equal 3. So, now let's look at this last piece. Complete the following statement according to the graph. as x approaches 3 from the left, which means from numbers smaller than 3. So we're coming this way from numbers smaller than 3. What are the y values getting closer and closer to as x approaches 3 from the left? Well, it's getting closer and closer to 2 from the left. Now the next question is what happens as x approaches 3 from the right, from numbers bigger than 3? What do the y values get closer and closer to? Well, the y values get closer and closer to 4. So, from the left, 2, from the right, 4. Now the last piece, we're going to actually use the equation that was in f of x. So we're going to use this. Use the equation and determine the y values that each piece approaches from the left and the right. So as x approaches 3 from the left, remember the function or the equation that has the numbers that are less than 3 is this one. So we're going to use this one. When x is greater than 3, which has the numbers bigger than 3, so numbers from the right, we're going to use this one. So as x approaches 3 from the left, we have 3 plus 3, absolute value, minus 4. So what's that? 6 minus 4 is 2. As x approaches 3 from the right. Now notice, we never get to 2, but we get closer and closer and closer. Now let's do the second equation when x approaches 3 from the right. And that would be negative 1/3 of 3 plus 5. Well, negative 1/3 times 3 is negative 1. Negative 1 plus 5 is 4. Look, those are the same, and those are the same. We did it graphically here. We did it analytically here. Now we're going to do the same thing for those other 3 functions. Let's look at g of x. What type of discontinuity occurred on g? Well, we already said it was a jump. And we said it happened at x equal negative 3. Is g of x defined at this x value? So does g of negative 3 exist? Well, let's go back and look. Sure, g of negative 3 exists. I got a closed circle there. When x is negative 3, y is 2. Excuse me, negative 2. So this is the bad part, having to go back and forth and scrolling. That's just, I know that's not good. We're right here. By investigating the constraints of the equation, the first piece of the graph will stop at x equals what, and the second piece will begin just past x equal what. So I'm on G. Now notice the first equation, the first piece of the graph stops at x equal negative 3 because this graph owns the fence at x equal negative 3. This piece starts just past x equal negative 3 because that graph doesn't own x equal negative 3. So the first piece of the graph will stop at x equal negative 3, and the second piece will begin just past x equal negative 3. As x approaches negative 3 from the left, what does the graph do? As x approaches negative 3 from the left, that means from numbers less than negative 3. So we're coming at it this way. As x approaches negative 3 from the left, the y values are getting closer and closer to, and in fact actually end up equaling negative 2. As x approaches negative 3 from the right, from numbers bigger than negative 3. This way. The y values here are getting closer and closer to negative 4. So we've got negative 2 on this one, negative 4 on this one. You notice these two numbers aren't the same. That's how you know you got to jump discontinuity. Using the equation. So let's go back and look at the equation. And I'm tired, I don't want to have to keep flicking back and forth. Here was the equation. That was the first one. This was the second one. As x approaches, let me do it this way. As x approaches negative 3 from the left. Now you're going to use this one because this one has the constraint that has all the x values that are smaller than negative 3. So substitute in negative 3 for x. Negative 3 plus 6 is 3. 3 squared is 9. Opposite of 9 is negative 9. Plus 7 is negative 2. G of x gets closer and closer to negative 2. As x approaches negative 3 from the right, this is the equation whose constraints had the numbers that were bigger than negative 3. So I'm going to substitute negative 3 in there. Negative 3 plus 3 is 0. Square root 0 is 0. Opposite of 0 is 0. And 0 minus 4 is negative 4. Please notice, graphically, algebraically, got the same thing. Graphically, algebraically, got the same thing. Now, you may be asking, so what's the point of this? We knew that that graph had a jump discontinuity. Did we have to see the graph? No, because we were able to look right here, which is the same as right here, based on whether you had the graph or you had the equation, and we were able to say from the left, the y value approached one number, and from the right, the y value approached another number. So they approach two different numbers. Those pieces are not going to connect at all. So I know that function is discontinuous at x equal negative 3. H of x. All right, let's go back and look at that one. What type of discontinuity occurred? We already decided that it was a point discontinuity, and that happened at, I believe, x equal negative 1. Is h of x defined at this value? Let's look at the graph. We're looking at h. Does anybody own the fence at x equals negative 1? Nope. So this function is not defined at x equal negative 1. So you're going to say undefined. I'm not going to keep going back and forth right now. I'm going to try to answer all the questions, then we'll go back and fill in the answers. Now the next question is, by investigating the constraints of the equation, the first piece will stop just shy of x equal negative 1, and the second piece starts just past x equal negative 1. I'm afraid I'm going to lose some of you, and I don't want to do that. We knew that the function was undefined. You can abbreviate that UND. We knew this was negative 1 and this was negative 1. All right, now we're going to look at this part here. As x approaches negative 1 from the left and from the right, we're going to look at the graph. As x approaches negative 1 from the left, those y values are getting closer and closer to that y value right there, which is 1. As x approaches -1 from the right, the y values are approaching 1 as well. Now, when we go down to that big box on the bottom where it says use the equation, I'm not going to flip back and forth to get the equation. I'm just going to look on my notes that I have in front of me so I can have the equation. Oh, whoops, I didn't go far enough, did I? So we got 1 on both of those. Now again, we're just using the equation of h. We are not using the graph, just the equation. As x approaches -1 from the left, I'm going to use the first equation, the one on the top, where x is less than -1. I'm going to substitute -1 in for x. -1 plus 4 is 3. Absolute value of 3 is 3. 3 minus 2 is 1. As x approaches -1 from the right, I'm going to use the second equation because that's where the function is greater, excuse me, the x values of the function are greater than -1. So I'm going to plug -1 in there. Opposite of -1 minus 1 squared plus 5. So what's that? -2 squared is 4. Opposite of 4 is -4. -4 plus 5 is 1. Now look, from the left, the graph said 1. The equation said 1. From the right, the graph said 1. The equation said 1. But the graph, excuse me, the function itself was undefined at x equal -1. So here's what I know. I know that those two pieces meet at an open circle because those y values are approaching the same number from both sides. But the graph is undefined there, so you got a hole. P of x, last one. What type of discontinuity occurred on P of x? I believe we said it was a point discontinuity at x equal -3. Is the function defined at this x value? Yeah, your x equal -3 does have a y value that goes with it. P of -3, you see that point down there, is -2. Now, I'm not going to flip back to the other one. I trust that after we've done 3 of these, you can take care of that yourself. By investigating the constraints of the equation, the first piece of the graph will stop just shy of x equal -3. And the third piece, that's wrong. The third piece, because the second piece is that point, the third piece will start just past x equal -3. That's not what I wanted. Now we're on this part. As x approaches -3 from the left, you go back and look at it, the y values are getting closer and closer to 2. Now notice it's not asking what is the y value when x is -3. It's asking what are the y values getting closer and closer to as x gets closer and closer to -3 from the left. Now the other piece, as x approaches -3 from the right, the y values looks like also are approaching 2. Now we use the equation. As x approaches -3 from the left, we're going to use that first function, 1/3 x plus 3. One-third of -3 is -1. -1 plus 3 is 2. As x approaches -3 from the right, we're going to use that third function. Absolute value of x, so absolute value of -3 plus 1. Oops, sorry, minus 1. Minus 2. Negative 3 minus 1 is negative 4. Absolute value of negative 4 is 4. 4 minus 2 is 2. You know what I should have done? I should have put this in right here. I should have put P of X approaches right here. That's just a little hat. And I should have put the same thing right here. I should have put P of X approaches. Guys, I should have done that on each one of them. Right here, I should have put H of X approaches. And here, H of X approaches. I am so sorry for my notation screw up there. So let's go back and get it right. Right here, I should have said F of X approaches. And right here, I should have said F of X approaches. And on that last one, well, I did it on the last one. Why did I not do it on the other two? Or other three? I'm sorry, I just made a brain fart there. Let's see here. Where are we now? Okay. After investigating the graphs and the equations of those four that we just did, what are some general conclusions that you can make about when a function will be continuous at A and when there will be point or jump discontinuities at x equals A? Okay, let's just go back for a minute and we're going to talk about each one of these graphs. Look at F. So you look at your graph and you look at the notes that you took a couple pages ago on F of X. So I'm just going to talk through this. As X approaches 3, and there's 3 right there. Now here's what we know. We know F of 3 is not defined. Listen, if a function is not defined at a point, there's no way the function can be continuous at the point. We're going to have to lift our pencil. So that's what blows this one up, is that the function's not even defined at x equals 3. Let's look at g of x. Is the function g of x defined when x equals negative 3? Sure is. It sure is. G of negative 3 we said was negative 2. Now, the next thing we looked at was what's the behavior of the graph from the left side of negative 3 and the right side of negative 3. Well, from the left side of negative 3, we found that the y values were approaching and in fact actually got to negative 2. But from the right, the y values were getting closer and closer to negative 4. Because those two pieces don't connect at all, you have a jump discontinuity. Jump discontinuity. Now, if you look right here, we said the graph was discontinuous at x equals 3. That one has a jump discontinuity as well. But you'll notice that the function is not defined at x equals 3. This one, g of x, the function was defined at x equals 3, or at x equals negative 3. So you can have a jump discontinuity regardless of whether the function is defined at that point or not. Let's go down to h. Now we could tell from h that we had a point discontinuity when x equals negative 1. Is this function continuous when x equals negative 1? No, because I'd have to lift my pencil there. If your function is undefined at x equals negative 1, that function is not continuous at x equals negative 1. Now my two pieces do meet at a closed circle there, so I do have a point discontinuity. So the function is discontinuous because the function is not defined at x equals negative 1. Now this last one, p of x. This is the one that's a little tricky. Is the function defined at x equals -3? Yep, it's -2. You got a circle right, or a closed circle right there. But what was the behavior of the graph as x approached -3 from the left and the right? Well, remember, from the left and the right, the y values got closer and closer to 2. Because where the function was defined and the y value that the function got closer and closer to were two different numbers, we have a discontinuity. That function is discontinuous. And remember, it's a point discontinuity because the two pieces connect at an open circle. So all that business is to say, what does it mean for a function to be continuous at any point x equals a? There are three pieces. The first thing, let's call our function f. F of x is defined at x equals a. Now remember, what does that mean? That means that f of a exists. The second important thing, the two pieces of the graph, and I can say graph or function, so let me say function. The two pieces of the function approach the same y value as x approaches a from the left and from the right. If you go back and look at p of x, let's look at what we said on this very first bullet item here. Was the function defined at x equal -3? Yep. F of -3, or excuse me, p of -3 was -2. Then let's look at the red bullet item here. Did the two pieces of the function approach the same y value as x approached -3 from the left and right? Yep. Approached 2. But the function was still discontinuous. Why? Well, it's because where the function was defined was not the same y value as the y value that the function approached from the left and the right. So the third piece says f of a must equal the y value that f approaches, let me see, that f approaches, yeah, as x approaches a from the left and the right. Guys, what you're doing right now, this is calculus. We are just not using calculus notation. Now I'm going to pause for just a minute because I got to get a drink of water, and I'm going to do some erasing. Oh, whoops. Huh, I forgot to erase, didn't I? Dummy. Now, what does it mean to have a jump discontinuity at x equal a? The function, heavens, may or may not be defined at x equal a. And the second one, and this is the big one for a jump discontinuity, the pieces approach different y values as x approaches a from the left and the right. That's the big deal about a jump discontinuity, is that the pieces approach different y values as x approaches a from the left and the right. Pause if you need to. I'm going to have to erase to have room to do the next one. Now let's talk about a point discontinuity. First, on the point discontinuity is the same as the jump. The function may or may not be defined at x equals a. So that's 1. 2. The pieces approach the same y value as x approaches a from the left and the right. But I've got to throw a third piece into this one. If the function is defined, this is defined. If the function is defined, f of a is not equal to the y value that the function approaches from the left and right of x equal a. Woo! Now thankfully the rest of this is just some practice problems. I think I'm tired of writing. For each of the functions below, determine the values at which the graph could be discontinuous. Let's look at number 1. Where could that graph be discontinuous? Well, if I graphed it, where would the fence be? At x equal -1. So this function could be discontinuous at x equal -1. So that's what I'm going to look at. Look at number 2. Where could this one be discontinuous? Well, also at x equal -1. Now, I'm not saying it is discontinuous, but that's the only place it could be discontinuous. Now, what else are we supposed to do? Determine if the function actually is continuous or discontinuous at those values. If the function is discontinuous, then classify the discontinuity as either jump or point discontinuities. Show your work and explain your reasoning for each. Now remember, the first thing you're going to do is you're going to say, is the function defined at x equal that particular number? So here, is g of -1 defined? Nope, because nobody owns the fence. G of x is, g of -1 is undefined. Now, I know right now that that function is discontinuous at x equals -1. What I don't know is what kind of discontinuity we have, jump or point. So now what I have to do is find what y value the function approaches from the left and the right of -1. As x approaches -1 from the left, I'm going to use the top equation. So as x approaches, I'm going to have to scoot over some. As x approaches -1 from the left, g of x approaches. Now I'm going to plug in -1 into that thing. -1 plus 4 is 3. 3 squared is 9. Opposite of 9 is -9. -9 plus 3 is -6. Now let's see what happens as x approaches -1 from the right. Now I have to use the second equation because those that constraint has the numbers that are bigger, the x values that are bigger than -1. Absolute value of -1 minus 3 minus 10. -1 minus 3 is -4. Absolute value of -4 is 4. 4 minus 10 is -6. Now let's go back up. Do we have a point discontinuity or do we have a jump discontinuity? Well, sorry, I erased my jump, but let's look at point. The function may or may not be defined at x equal a. And then look at the purple. The pieces approach the same y value as x approaches a from the left and the right. That's what happens here. The y values approach the same number as x approaches a from the left and the right. So what we've got is something like this. It's going to come in whole, and then it's going to come right back out. What kind of discontinuity? That's a point discontinuity. So you're going to say point discontinuity at x equals -1 because g of x approaches -6 as x approaches -1 from the left and the right. Now remember though, the other issue is if the function approaches the same value from the left and the right, is the hole filled in there? No, because we already figured out that g of -1 was undefined. And g of -1 is undefined. Okay, next problem. Oh, I don't know why I erased that. We know that this function, if it has a discontinuity, it's going to be at x equal -1. So remember, first question, what is g of -1? Does that exist? Yep, because somebody owns the fence. The second dude owns the fence. So g of -1 is -1 plus 3 minus 4. Let's see, -1 plus 3 is 2. Absolute value of 2 is 2. 2 minus 4 is -2. So the function's defined there. Now let's see what happens as x approaches -1 from the left and the right. As x approaches -1 from the left, g of x approaches, so we're going to use this one because this x has the numbers that are less than -1. -2 times the absolute value of -1 plus 3 plus 2. Let's see what that equals. -1 plus 3 is 2. Absolute value of 2 is 2. Times -2 is -4. And -4 plus 2 is -2. And as x approaches -1 from the right, g of x approaches, we're going to use the second equation because the second equation has constraints that have the x values that are bigger than -1. Absolute value of -1 plus 3 minus 4. -1 plus 3 is 2. Absolute value of 2 is 2. And 2 minus 4 is -2. Oh, look at this. Is this function continuous at x equal -1? Yes. So here's what we're going to say. Therefore, you ever seen therefore written like that? G of x is continuous at x equal -1 because g of -1 equals -2, which equals the y value that the function approaches. That's approaches. As x approaches -1 from the left and the right. What it means is the open circle created by those two pieces coming together at the same place is filled in. That open circle is filled in. All right, we got one more page. I know this is, dang, this is long. Let's look at this one. This function could be discontinuous at two different places. This function could be discontinuous at x equals 3 and at x equals 5. So we're going to have to check them both out. Let's start with x equals 3. Does h of 3 exist? Yes, because the fence x equal 3 is owned by this one. So h of 3 is 3 squared minus 2 times 3. What's that, 9 minus 6? So that's step 1. Now step 2, as x approaches 3 from the left, h of x approaches what? And as x approaches 3 from the right, h of x approaches what? So let's start with from the left. We're going to start with this one. As x approaches 3 from the left, this is the equation you're going to have to use because these constraints show the numbers, the x values that are less than 3. So I've got 2 times 3 minus 3. That appears to be 3. As x approaches 3 from the right, I'm going to have to use this one because this has the numbers that are bigger than 3. Now, here's what you may say. That has numbers that are bigger than 3 too. Yeah, but it doesn't come up all the way to x equals 3, so you can't use that one. So we're going to use that second equation, 3 squared minus 2 times 3. 3 squared is 9, 9 minus 6 is 3. Ha ha, what do you see? What do you see? Okay, I'm going to just have to write my conclusion down here. H of x, therefore, h of x is continuous at x equals 3 because h of 3 is equal to 3, which is the y value that the function approaches as x approaches 3 from the left and the right. Now we've got to go back and do that same equation, or excuse me, the same process to determine if this function is continuous or discontinuous at x equals 5. I just stopped and did some erasing. Now let's try at x equals 5. Does h of 5 exist? Yes, because 5 is owned. That fence at x equals 5 is owned, and it's owned by this equation right here. Absolute value of 5 minus 3 plus 2. What's that? 2 plus 2 is 4. Now let's see what happens as x approaches 5 from the left and the right. As x approaches 5 from the left, h of x approaches, we're going to have to use this equation. 5 squared minus 2 times 5. What's that? 25 minus 10. I believe that is 15. As x approaches 5 from the right, h of x approaches, I'm going to have to use this one. 5 minus 3 plus 2. That's 5 minus 3 is 2. Absolute value is 2 plus 2 is 4. So, is the function continuous at x equals 5? No, because as x approaches 5 from the left and x approaches 5 from the right, the y values approach different numbers. So they don't even connect. The two pieces do not connect. Therefore, the function is discontinuous and you have a jump discontinuity. So h of x has a jump discontinuity at x equal 5 because, I'll do it down here, the function approaches different y values from the left and the right. All right, we got one more. Man, have we had a lesson that's this long? Shoo. One more. For what values of a and b will the function below have point discontinuities at x equal -3 and x equal 2? Remember, point discontinuities. I don't care if the function's defined, but what has to happen as the function approaches those numbers from the left and the right, the y values have to approach the same number. So let's start with x equal -3. As x approaches -3 from the left, f of x is going to approach, now -3 from the left, I'm going to have to use this one. 2 times -3 is -6, plus 3 is -3. As x approaches -3 from the right, f of x approaches, now I have to use this one. Now substitute in -3 for x, so that'll be -3a plus 3b. Now remember, for this function to have a point discontinuity at x equal -3, the y values that the function approaches from the left and the right must be the same. So -3 has to equal -3a plus 3b. Now you say, well, I don't know what to do with that. Well, it's because you can't do anything. You've got one equation and two variables. Let's do the x equal 2 part. I'm going to have to erase so I don't have to keep scrolling up and down. At x equal 2, again, I don't care if the function's defined. It isn't here, but I don't care if it is or not. What I want to know for a point discontinuity is, does the function approach the same y value from the left and the right of x equal 2? As x approaches 2 from the left, f of x approaches. 2 from the left is going to be this one. That's going to be 2a plus 3b. As x approaches 2 from the right, I have to use this one. F of x approaches, let's see, that's 1/2 of 2 squared, so half of 4 is 2. 2 plus 6 minus 1, believe that's what, 7? So in order for this function to have a point discontinuity at x equal 2, those y values must be the same. So 7 must equal 2a plus 3b. Look what you've got. You got a system of equations that you can solve by substitution or elimination. I stopped and erased for a minute. Now, let me see here. I think I'm going to use elimination. What if I multiply this equation by -1? Then I'll have, whoops, I won't have that, will I? 3 equals 3a minus 3b. The other equation I did not touch, 7 equals 2a plus 3b. Add them up. 10 equals 5a. Woohoo! A equals 2. So what's b? Well, I'm going to stick b equal to, I'm going to stick a equal 2 right there because that looks pretty easy. 7 equals 2 times 2 plus 3b. So 3 equals 3b. So b would have to equal 1. So if a equal 2 and b equal 1, then this function would have point discontinuities at x equal -3 and x equal 2. That was one long lesson. Hope it goes smoothly for you. We'll talk about it next time if you have any trouble.